A computer program beat a human brain at the ancient Chinese board game of Go. The final score 4-1, a triumph for artificial intelligence equipped with human intuition.
The victory of a program over a human in the ancient board game Go has sparked intrigue and, in some cases, concern. It shows that a machine has approximated human intuition and outsmarted the best human brain in the game. It's something that scientists hadn't expected to happen for at least another decade, and it's a giant leap for artificial intelligence, showing that machines can learn on their own.
This was the moment a computer called AlphaGo beat a master of the ancient Chinese game Go. It's not the first time a grandmaster's been humbled by a machine. But what makes AlphaGo different is that it's the first demonstration that machines can truly learn and think in a human way.
AlphaGo used reinforcement learning and neural networks to mimic the learning process of a human brain. Keep in mind that the ancient Chinese game Go has as many more possible moves than chess as there are atoms in the entire universe. So there's no way of just calculating every possible move on the board. That's practically impossible.
So the way we start off training AlphaGo is by showing it 100,000 games that strong amateurs have played that we've downloaded from the internet. And we first initially get AlphaGo to mimic the human player. But of course, ultimately, we would like AlphaGo to be stronger than human amateurs and compete with the top professionals. So the way we do that is, after we take that first version that's learnt to mimic human play, we then allow it to play itself 30 million times on our servers, and using reinforcement learning, the system learns to improve itself incrementally through it avoiding its errors and increasing and improving its win rate against older versions of itself. And after all these games, then you end up with a new version that can beat the old version, the original version, around 80–90% of the time.
Technically, the reinforcement that DeepMind uses is model-free, meaning that it doesn't need a structure or set of rules to learn. According to MIT's take on the Google algorithm, the neural network, in theory, should be able to access an external memory in a manner that mimics the short-term memory of the human brain. In a way, it almost seems like our brain's design might be the most efficient way for the creation of local intelligence. Who would have guessed? So that's all good. What about this general purpose term? What does that actually mean? Well, because the machine learns from raw experience and data, it can perform well across a wide variety of tasks, straight out of the box. Okay, so that's enough talk. Let's watch the system in action, learning how to play Breakout. And remember, the machine didn't have any foreknowledge as to what task it was going to complete. It had to figure out how to do everything only from its own experience.
Is the machine before training. So this is literally the first time the machine has ever seen this data stream, and it's controlling the green rocket here, and you can see it's losing its 3 lives immediately. So it's basically terrible at the game, as you would expect. Now, after training, this is like overnight. We leave it playing the game overnight on a normal computer, so for about 8 hours. You come back in the morning, and now it's superhuman level. So now the machine can play Space Invaders better than any human can. It's modeled the world, the game world, so well. It knows where the Space Invaders will be ahead of time. So as the Space Invaders speed up, when you get less of them on the screen, it fires the final shot as a kind of predictive shot of where the final Space Invader will be in a few seconds.
So what could general purpose AI be used for?
We'd love to use these types of algorithms for things like healthcare and science, and improve the speed of breakthroughs in those areas by helping human experts achieve more.
In a number of interviews, Dennis has talked about applications in healthcare, smartphone assistance, and robotics as possible applications for general AI. Some other applications of such AI include online customer service, computer vision, finance, general computer science, and news publishing and writing.
How many of you are creatives? Designers, engineers, entrepreneurs, artists, or maybe you just have a really big imagination? Show of hands. Okay, that's most of you. I have some news for us creatives. Over the course of the next 20 years, more will change around the way we do our work than has happened in the last 2000. In fact, I think we're at the dawn of a new age in human history. Now, there have been 4 major historical eras defined by the way we work. The hunter-gatherer age lasted several million years. And then the agricultural age lasted several thousand years. The industrial age lasted a couple of centuries. And now the information age has lasted just a few decades. And now today, we're on the cusp of our next great era as a species. Welcome to the augmented age. In this new era, your natural human capabilities are going to be augmented by computational systems that help you think, robotic systems that help you make, and digital nervous system that connects you to the world far beyond your natural senses. Generative design tools use a computer and algorithms to synthesize geometry, to come up with new designs all by themselves. All it needs are your goals and your constraints. I'll give you an example. In the case of this aerial drone chassis, all you would need to do is tell it something like it has 4 propellers, you want it to be as lightweight as possible, and you need it to be aerodynamically efficient. And then what the computer does is it explores the entire solution space, every single possibility that solves and meets your criteria, millions of them. It takes big computers to do this. But it comes back to us with designs that we, by ourselves, never could have imagined. And the computer is coming up with this stuff all by itself. No one ever drew anything, and it started completely from scratch. And by the way, it's no accident that the drone body looks just like the pelvis of a flying squirrel. It's because the algorithms are designed to work the same way that evolution does. Now, what's exciting is we're starting to see this technology out in the real world. We've been working with Airbus for a couple of years on this concept plane for the future. Now, it's a ways out still, But just recently, we used a generative design AI to come up with this. This is a 3D printed cabin partition that's been designed by a computer. It's stronger than the original, yet half the weight. And it'll be flying in the Airbus A320 later this year. That's what I'm talking about, technology amplifying our cognitive abilities so we can imagine and design things that we were simply out of our reach as plain old unaugmented humans. So what about making all of this crazy new stuff that we're going to invent and design? I think the era of human augmentation is just as much about the physical world as it is about the virtual intellectual realm. So how will technology augment us? In the physical world, robotic systems. Okay, there's certainly a fear that robots are going to take jobs away from humans, and that is true in certain sectors. But I'm much more interested in this idea that humans and robots working together are going to augment each other and start to inhabit a new space. This is our applied research lab in San Francisco, where one of our areas of focus is advanced robotics, specifically human-robot collaboration. And this is Bishop, one of our robots. And as an experiment, we set it up to help a person working in construction doing repetitive tasks. Tasks like cutting out holes for outlets or light switches in drywall. So Bishop's human partner can tell him what to do in plain English and with simple gestures, kind of like talking to a dog, and then Bishop executes on those instructions with perfect precision. We're using the human for what the human is good at, right? Awareness, perception, and decision-making, and we're using the robot for what it's good at, precision and repetitiveness.
Meet Sawyer, the revolutionary new high-performance collaborative robot from Rethink Robotics, designed to execute machine tending, circuit board testing and other precise tasks that are impractical to automate with conventional robots. Sawyer gives manufacturers the high-performance automation they need for a wider range of tasks, while maintaining the critical flexibility, safety and interactive user experience that is necessary for working successfully alongside, and with, people. Sawyer weighs only 19 kilograms, with a 1.4-meter reach, that can maneuver into the tight spaces, and varied alignments of work cells designed for humans. Its motion control allows it to feel its way into fixtures or machines, even when the position varies slightly. This means that Sawyer can work precisely in semi-structured environments, operating safely next to human co-workers. And Sawyer adapts to real-world variability on the plant floor. It's agile enough to change applications quickly, and performs tasks like humans do. Sawyer has a head camera for wide-view applications, and a Cognex camera in its wrist, that enables the robot positioning system, and other complex vision tasks. And its iconic, expressive face screen design helps it communicate happily with co-workers. One of Rethink Robotics' most important markets for Sawyer is China. Scott Eckert, President and CEO of Rethink Robotics, explained that Chinese manufacturers are facing similar challenges to their counterparts around the world, including rising wages and labor shortages.
So, as computers are going to augment our ability to imagine and design new stuff, robotic systems are going to help us build and make things that we've never been able to make before. But what about our ability to sense and control these things? What about a nervous system for the things that we make? Our nervous system, the human nervous system, tells us everything that's going on around us. But the nervous system of the things we make is rudimentary at best. For instance, a car doesn't tell the city's public works department that it just hit a pothole at the corner of Broadway and Morrison. A building doesn't tell its designers whether or not the people inside like being there. And the toy manufacturer doesn't know if a toy is actually being played with, how and where, and whether or not it's any fun. Look, I'm sure that the designers imagined this lifestyle for Barbie when they designed her, right? But what if it turns out that Barbie's actually really lonely? If the designers had known what was really happening in the real world with their designs, the road, the building, and Barbie. They could have used that knowledge to create an experience that was better for the user. Now what's missing is a nervous system, connecting us to all of the things that we design, make, and use. What if all of you had that kind of information flowing to you from the things you create in the real world? The good news is we're working on digital nervous systems that connect us to the things we design. We're working on one project with a couple of guys down in Los Angeles called the Bandito Brothers and their team. And one of the things these guys do is build insane cars that do absolutely insane things. These guys are crazy, in the best way. And what we're doing with them is taking a traditional race car chassis and giving it a nervous system. So we instrumented it with dozens of sensors, and then we put a world-class driver behind the wheel, took it out to the desert, and drove the hell out of it for a week. And the car's nervous system captured everything that was happening to the car. We captured 4 billion data points, all of the forces that it was subjected to. And then we did something crazy. We took all of that data and plugged it into a generative design AI that we call Dreamcatcher. So what do you get when you give a design tool a nervous system and you ask it to build you the ultimate car chassis? You get this. This is something that a human could never have designed, except a human did design this. But it was a human that was augmented by a generative design AI, a digital nervous system, and robots that can actually fabricate something like this. So if this is the future, the augmented age, and we're going to be augmented cognitively, physically, and perceptually, what will that look like? Thanks to our augmented capabilities, our world is going to change dramatically. We're going to have a world with more variety, more connectedness, more dynamism, more complexity, more adaptability, and, of course, more beauty. The shape of things to come will be unlike anything we've ever seen before. Why? Because what will be shaping those things is this new partnership between technology, nature, and humanity. That, to me, is a future well worth looking forward to. Thank you all so much.